Today's video is on pulleys, one of the most difficult sections of the AS mechanics course, particularly with examples like this where instead of being something over a pulley like that, we've now got a pulley where something is on a table, so we're going to have to consider resolving in a horizontal and a vertical direction. So as I go through this, I'm going to start drawing the parts of the diagram that are needed. So two particles A and B of masses 0.4, 0.8 respectively, connected by a light inextensible string. That basically just tells us everything is normal. Particle A lies on a rough horizontal table 4.5 meters from a small pulley, smooth pulley, which is fixed at the edge of the table. So here I need the table. Pulley fixed at the edge of that table. And we have this mass A of 0.4 kilograms, which is going to have gravity of 0.4 g acting on it. And it's connected by this string. And the distance here is 4.5 meters from the pulley. A pulley is fixed at the edge of the table. The string passes over the pulley and B hangs freely. So here is B hanging freely with the string taut 0.5 meters above horizontal ground. So here is particle B with mass 0.8 kilograms. And therefore gravity 0.8 g acting downwards. And we also have the horizontal ground to include. So although this is not to scale, I'm going to put in my horizontal ground, and it is 0.5 meters above the horizontal ground. A frictional force of magnitude 0.08 g opposes the motion of particle A. So we were told that the table was rough. That means that there is friction on the table, and we're told that that particular force is 0.08 g, pulling against the motion of A. The system is released from rest. That means that it starts stationary, as if the pulley is clamped or something, and then when it says it's released from rest, then everything will start moving. And if we look at how this works, obviously this will start accelerating downwards, so we're going to have an acceleration downwards, which we'll call A. And because the string is inextensible, this acceleration downwards will be exactly the same as the horizontal acceleration here. So I can mark them both in and call them both the same letter. We also have a tension in the string. So the tension in the string is acting forwards, pulling this forwards, which means that it's pulling backwards on the pulley itself. And we have the same down here. It's acting downwards on the pulley, which means that the block B experiences it acting upwards, pulling upwards on that. So part A, find the acceleration of the system. This is what we've marked as A here. So first of all, I'm going to look at block A. So just label your working as normal. Block A, resolve horizontally, because that's the direction of travel. Just thinking about block A itself, and force equals mass times acceleration. The thing that's acting forwards on A is the tension in the string. The thing that's acting backwards is the 0.08 g. This downwards force acting on A doesn't affect the horizontal motion. It's not part of that. So we've got the mass, which is 0.4, times by the acceleration A. Then separately thinking about B, and this is always the way we start things with pulleys, is think about the two different sides of the pulley separately. Here we need to resolve vertically. I'm going to talk about downwards as positive because A is positive that way and therefore positive this way, the acceleration. Again, force equals mass times acceleration, so I have 0.8 g pulling the B down, and it's pulled upwards by the tension in the string, and that will be 0.8 mass times by acceleration. And what we have here is a pair of simultaneous equations, and as normal with pulleys, you'll see that this happens virtually every time. We can add our two simultaneous equations to get rid of T, the tension in the string. So that will give us 0.8 g minus 0.08 g t plus minus t cancels them out. Adding these two together, that gives us 1.2a. So putting all of that together with numbers, so 0.8 times 9.8 is gravity, minus 0.08 times 9.8 for gravity is, so 7.056 equals 1.2a, and therefore a equals 5.88 meters per second squared. And that's the acceleration. In the book example, it gives that as 0.6 g, which is the same thing. They just haven't, they've left the g in the answer. So part B asks for the time taken for B to reach the ground. Well, now we know how fast B is accelerating, we can do suvat for B itself. So for B, we know that it's got to reach the ground, so the distance travelled is 0.5 meters. Its initial speed is 0. Final velocity we don't know, and we don't want to know. A acceleration is this 5.88 meters per second squared, or 0.6 g. And time taken is what we're trying to find out. So we've got S, U, A, and T. We're going to need S equals UT plus half AT squared. So that gives us 0.5 equals 0 times T, so that's 0. Half times 5.88 times by T squared, which means that T squared equals 0.17, etc. T equals 0.412, etc. So we're going to call that 0.41 to two significant figures, because we use gravity to do significant figures here. So 0.41 seconds. Part C, that's part B. Part C, find the total distance travelled by A before it first comes to rest. So what we're going to have to consider here is two sections of motion. We've got, first of all, the motion as it's pulled down by A. So in that time, it will be moving 0.5 meters, being pulled along by B until B hits the floor. And at that point, it's going to be moving with a certain velocity. And at that point, everything about the system changes, because it will no longer be being pulled forwards, because there will be no more tension in the string, because B has now hit the floor. So we are talking about this now moving forwards under its own momentum. That's the only reason it's moving forwards, and it still has this frictional force acting behind it. So if we think about A then, so for A, it moves 0.5 meters until B hits the floor. And then at that point, we have the block A with the force acting backwards on it, 0.08 g. No force acting forwards at all. We're going to have to calculate a new acceleration, and all we need here is a velocity. It still weighs 0.4. We need to know its velocity as it starts here, so that we know how long it's going to take to slow down. So if we think about, first of all, the acceleration at this point, F equals ma again. Force is acting on this. Again, let's treat the acceleration as going forwards. So the force is minus 0.08 g is the mass times by the acceleration, so 0.4a. That means that A equals 0.2 g, which is 1.96 meters per second squared. There should be minus in those because its acceleration is actually backwards now. It's decelerating. So if we think about that, and then we also think about the speed that A was moving at, in order to do that, we have to think of the velocity that B was moving at as it hit the floor. So we'll go back to this B situation and find the speed that everything was moving at as B hit the floor. So again, we have this S equals 0.5, U equals 0, V equals question mark, and A equals 5.88. And we can use V squared equals U squared plus 2AS. V squared equals U squared plus 2AS. So therefore, V squared equals 0 plus 2 times 0.5 times 5.88. Therefore, V squared is 5.88. V equals 2.42, or root 5.88. And now we consider A again. So for A, after B has hit the floor, we've got this acceleration of minus 1.96 meters per second squared. So we want a distance traveled. That's what we're trying to find out. We've got a initial speed of 2.42. That's going to call it root 5.88 to keep things accurate. We've got a final velocity that we don't know about and don't need to know. The acceleration is minus 1.96 meters per second squared. And that should, we do need V because we want to know when it comes to rest. So I was going to say we need T, but we don't. We know that the whole thing is going to come to rest, so we need V equals 0 here. So the one we can choose to use this time needs, again, V, U, and S. So let's use V squared equals U squared plus 2AS. We have our V equals 0, our U equals root 5.88, plus 2 lots of minus 1.96 times S, and we're trying to get S on its own. So S equals root 5. That was meant to be squared, U squared. So S equals 5.88. I'll leave the minus signs in. Bring that to the other side. We've got minus 5.88 over 2 times minus 1.96. And that gives us minus 5. It actually gives us 3 over 2. It's 1.5. So it's moving 1.5 meters. So in total, you have to remember that A, first of all, moved along until B hit the floor, and then it started decelerating, and that deceleration process took it 1.5 meters. So in total, which is what the question asked for, total distance traveled by A before it comes to rest, in total we've got A moves 0.5 meters plus 1.5 meters, 2 meters traveled in total. That's to 2 significant figures. And we can see that in that it hasn't hit the pulley yet, and so that's why this was significant, this 4.5 meters here. If this block had been closer to the pulley than 2 meters, it wouldn't have had time to slow down to rest. It would have hit the pulley first and been stopped by that pulley. Just to correct my answer there, it should be 2.0 to 2 significant figures. I know that it is accurately 2, so I can give it to 2 significant figures with the decimal place and the 0 afterwards there.